you would expect there should be also some deformation of the Liouville theory or the Q-deformed Liouville theory, which corresponds to some sort of elliptic deformation on this side. And this is the problem we tackled with Iqbal and Yao. And independently, also Fabrizio Nieri constructed the same conformal blocks using more or less the same techniques. So here's a short outline. So I just want to, I don't probably need to talk about AGT conjecture or AGT relation, but okay, I just briefly in 2 slides we'll talk about that and talk about how you embed, how we think about this lift in a different way and talk about what we call like in a gauge-Liouville triality in a paper with Aganegich, Hausi, and Shakirov. And then in this context, it will be easy to understand how to lift how to deform it elliptically. So Gayotto constructed this generalized quiver theories by compactifying the 6-dimensional, twisted 6-dimensional 2,0 theories of n-1 type on a punctured Riemann surface. And here I'm just going to restrict when you have only SU2 theories, when we have A1 type. And as a prototypical example, I've chosen here SU2 with 4 flavors. So that will be the sphere with 4 punctures. So later, after work of Gayotto, Alday, Tachikawa, and Gayotto and Tachikawa propose a relationship by considering different compactifications of the 6-dimensional theory and realized the instant partition function on the gauge theories, on this quiver gauge theories, is related to the conformal blocks of the Liouville theory on this same Riemann surface, where you need to insert a primary field to these punctures. And basically, the dictionary is the chiral conformal blocks will correspond to instanton partition functions, and the 3-point functions are related to the one-loop perturbative part. And the masses of the hypermultiplets you have corresponding to the punctures are related to the external momenta when you compare the conformal blocks. And Coulomb branch parameters are your internal momenta running in the conformal block. The coupling constant is related to the instanton counting parameter is related to swinging parameters. And the equivalent localization parameters, which people have used to deform R4 to this omega background, are mapped to the Liouville parameters. Okay? So Dijkgraaf and Waffa propose a type 2b prescription why this correspondence should be related by connecting it to geometric transition, which is a well-understood phenomena in topological strings especially. But here I just want to talk about some sort of mirror version of that. So if you, again, want to think about or restrict for the sake of argument to SU2 with 4 flavors, then geometric engineering tells you you should start or you should compactify your type 2A theory on a local P1 cross P1 blown up at 4 points. So the local P1 cross P1 would correspond to pure SU2 theory, and each blow-up will support a multiplet when you wrap a D2 brane on that exceptional curve. So one thing you can do is you can actually set the values of certain Kähler parameters, certain Kähler classes, in this case exceptional Kähler classes, to a multiple, integer multiple of this equivalent, one of the equivalent localization parameters. And then the geometry looks, and small, when you're not taking the large n limit, then the geometry looks singular, but you can go through the geometric transition inversely and think this as it's coming from some deformed geometry where you actually wrap certain number of branes on that local S3. Okay? And that should be familiar if you, this is more or less the same construction if you think in terms of the vortex strings in type 2A, where you start with this construction written to engineer Seiberg-Witten theories with the NS5 branes and the 4 branes suspended between them. And if you move your the 4 branes which are, which are extending to infinity with the internal D4 branes. So you can move this NS5 brane, and then you can suspend between the D4 branes and this what I call NS5 prime, these D2 branes. And these are, the vortex strings. And this is actually the point where the Higgs branch meets the Coulomb branch, and there is this, you would expect naively that, A should be equal to m vector. However, there is this shift by epsilon times integer vector due to the deformation of the omega background. Okay? And you can just think all this geometry, instead of in type 2a, also fibered with a circle. So then the geometric transition would imply that the closed partition function is related to the open partition function. In fact, they're equal. But if you translate the closed partition function in topological strings, that's related to the instanton partition function. On the other hand, the open amplitude is related to the vortex partition function. And the equivalence between them at that particular limit would imply the equivalence between the vortex partition function and the instanton partition function. So you can compute both sides, this theory on R2 times S1, and this is R4 times S1. You can both introduce this omega type deformation and use localization techniques to compute them. And if you do that, eventually when you localize it, they reduce to matrix models. And these matrix models can be solved. Moreover, the matrix model you get for this local three-dimensional theory is exactly the same matrix model which Dostoevsky and Fateev use to represent the conformal blocks. So if you do this in this one-dimension higher case, then you get the Dostoevsky-Fateev Coulomb gas representation for the Q-deform Liouville theory. So then you will establish actually this what we call the triality, not triality in the usual sense. Maybe it's some people might object that, but triality in the sense that they are three corners. One of them is a five-dimensional gauge theory, the other is a vortex partition function, and the third corner being the Liouville conformal block. So before I said, this relationship is, if you lift it to one dimension higher, this relationship gives you the more or less AGT conjecture on the nose. You may not need to do too much because you just do the computations on each side and compare the expressions, and they turn out to be identical. Up to one caveat, which I will come back later. So to go into a little bit more technical and in details, so this is the action of the Liouville theory, and the Liouville field has a free field representation, and the Fourier modes satisfy the usual Heisenberg algebra. And the Dostoevsky integral representation is for an endpoint function. You just include two more, and you put your primary fields as well as some screening charges to absorb the momenta, and you just perform this counter integral. So one of the questions about performing these conformal blocks was the choice of the contour. And it turns out the contour is not that difficult, and it's just they're circling 0 and the other insertion points and leaving the point, the other last insertion point infinity untouched. And you can represent the primary fields as vertex operators, and the screen charges have a similar representation. So if you just plug them in this integral, you will end up with a matrix integral. And you can just write it down by Wick's theorem, by Wick contraction between the vertex operator. And if you look at if you just compute this integral, then you can see this is, in this case, this is going to give you the Liouville conformal blocks. And then that's related to the 4D instanton partition function. And in 90s, people have, for different motivations, introduced some Q deformation of this algebra by deforming the Heisenberg generators in a Q and T dependent way. So here, Q and T can be related to each other. You can write T equal to Q to the beta, where beta is a complex number. And the beta is related to B of the Liouville theory, Liouville parameter, such that B is minus B, beta is minus B squared. Okay? So if you just set T equal to Q, that's when, you know, then that actually reduces to, sorry, when you just take Q and T with this condition to 1, then you cover the usual Heisenberg algebra. And if you actually like, you know, okay, so moreover, it's not only enough to deform the Heisenberg algebra, you also need to deform the vertex operators and the screening charges. So if you deform in addition to deforming the Heisenberg algebra in this way, both of them, so you can, then that gives you the like, you know, Q-deformed conformal blocks. And again, you know, you can just plug in these like vertex operators and screening charges into this integral, use the Wick's theorem, and you will end up with a matrix integral of this form where you replace this, this like, you know, differences by ratios, and this is like, you know, the Q-deformed Pohammer symbol. So this is the basic Q deformation, and again, if you set Q equal to 1, or this will reduce to the usual statement, or when T equal to Q, okay? So, and this you can match by, and these integrals can be computed by residue theorems, and you can actually show with this choice of the contours, the residues can be labeled, or the poles can be labeled by Young diagrams, and you can actually convert the integral into a sum over Young diagrams. And that Young diagram is matching this famous Young diagram computation of instantons if you go to the limit when the Coulomb branch parameters are related to the half of the hypermultiplied masses as I shown before. And then you can show this is A in this, I mean, producing this instanton result, and B, it's also related to matrix integral you will get by localizing on these vortices. Okay, so here we established then at this limit, then the 5D partition function is related to the vortex partition function, which is actually another way of saying this is actually the Q-deformed Dovzhenko-Fotev integral. Okay, so here I have a remark. As I said, like, you know, this is up to a caveat, and the caveat is, so if you take a 4-point function, or let me just actually say something better, like if you take a 5-point function, AGT conjecture tells you that's supposed to be related to the instanton partition function of SU2 times SU2 with a bifundamental method connecting these two gauge groups, as well as two fundamental multiplets associated to each gauge group. So it's like a certain method content and related to the 5-point function. However, the 5D partition function we found here is not this gauge theory, but rather SU2 with 6 flavors. And you may think, okay, they are completely unrelated theories. However, if you, as I said, if you just embed everything in type 2A in terms of the geometric engineering, they are related to each other. They are related by the so-called fiber-base duality. If you engineer this theory, SU2 times SU2, you have to pick a base which consists of 2 P1s and fiber over that A1 singularities. However, if you just exchange the roles of the P1s and fibers and base, then that will be 1 P1 with an A2 singularity fibered over that. And that's actually the SU2, SU3 theory. So these are like, you know, actually, I mean, and refined topological vertex computation actually show that the partition functions are in fact equal to each other, but they're expanded in different ways. So essentially, this relationship we found with Aganagic, Auzi, and like Shakirov, combined with fiber-based duality, can be regarded as a physical proof. I don't want to like, you know, say too ambitiously it's a proof in general, but up to this like, you know, physical argument, this is a proof of the AGT conjecture in the Q-deformed limit, or in the Q-deformed lift. Okay? So what can we do more? What we can do is, I mean, this is the geometry we started, again, for SU2 with 4 flavors. And as I mentioned before, Hollywood, Iqbal, and Wafa realized that you can actually, instead of writing and okay, this is probably known. The toric diagrams are related to this PQ web diagrams in type 2b context. And instead of like, writing down this PQ web on drawing this PQ web on a plane, you can also draw it on a cylinder. And that means you will identify this external legs of the toric diagram, this one and that one, and this one and this one, and kind of introduce like, a torus. Because this is torus because the external lines in the toric diagram will constitute of the disk, as you know. And if you combine two disks together, that's a P1. And then this is actually like in a pinch torus with like a bunch of P1s connected in in the affine quiver of A. And that's supposed to be the F theory. This introduces an elliptic vibration with a section on the geometry, and then you can lift it to F theory. And here, in terms of, if you want to like also think in terms of like Seiberg-Witten theory in its connection with the integrable systems, you start with rational integrable systems related to the 4D Seiberg-Witten theory. You Q-deform it, you go to trigonometric, and this last one is going to make you elliptic. Okay, so then we have to deform the algebra or this Q deformation. So how do we do that? So you just go up to literature, and Sayoto actually did it already. So he actually wanted to look at some elliptic deformations of the so-called Ihara-Miki algebra, and these algebras appeared on a number of different studies related to AGT conjecture in the literature before. So I don't want to go into that direction, but he wanted to introduce this elliptic deformation to the Ihara algebra, which is also has some relationship to the integrable systems and writing down the Hamiltonians for those elliptic integrable systems. But I just want to like, borrow his techniques and apply. So he also constructed like, along the way, how you need to deform the vertex operators. So if you have a vertex operator, very generically, and with this free field representation, and you have this Fourier modes, and these H's satisfy the Q-deformed Heisenberg relationships before. So what he proposes, yet another deformation. You remember, like, this 1 minus q to the n over 1 minus 2 to the n was the Q deformation. In addition to that deformation, he introduces elliptic parameter p, and you have to like multiply with an extra factor 1 minus p to the n. However, he realized that's not enough. And you can also like, see it holistically in an easy way. If you think in terms of the theta function can be written in terms of 2 Q Pohammers. Not just one, but two. So one set of like Heisenberg operators is not enough. So you should be able to also reproduce the second Pohammer in theta functions to get something elliptic. So he introduced another set of Heisenberg operators which commute with the original ones, A, and they satisfy a similar relationship up to this shift. And you can see actually this relative shift is creating this shift in the modular parameters in the elliptic functions. Okay, so, but how the elliptic vertex operators look like? So given this Fourier expansion, you have to then introduce a vertex operator which is written in terms of a Heisenberg algebra, and that's multiplied with another vertex operator that's like, written in the B Heisenberg algebra. So here is explicitly the forms, and if you are careful, there are sign changes in Z's, again, ensuring like, when you compute the normal product, you can actually get appropriate products so that they can combine into an elliptic function. So they are like, tuned in such a nice way, and as I showed you, like, there's like, ratio, the differences were replaced by Q Pohammers in the Dovzhenko-Foteyev integrals, but now they are like, deformed by these double elliptic gamma functions. So everything is now ellipticized, like, using Sayoto's like, construction. But is this deformation the deformation we need? So we wanted to check that, and I also like to emphasize also Fabrizio Nieri established, again, using the same methods, like similar conclusions. So what we have checked is we went back and computed using refined topological vertex the instanton partition function of the 6D theory, and realize, I mean, if you don't change the contours in the Dossenko-Fateh integral, if they are the same as in the case of the Q deformation, and as in the usual case when you're only computing the Liouville conformal blocks, you just match that conformal block to the 6D instanton partition function. Okay, before I end, I also want to add one final remark that actually this elliptic deformation, this algebraic elliptic deformation, because there has been some work by Awata and his collaborators understanding refined topological strings, especially the refined topological vertex, from algebraic point of view in terms of, again, the Ihora algebra. And if you compute this open amplitude, this is the resolved conifold, an open amplitude with some boundary conditions on how the holomorphic maps on the Lagrangian planes, you can't just write them as, algebraically as a vector, and then this is just overlap between two vectors. You can write it. And if you just, take this exponential, it looks like, a vertex operator. If you elliptically deform it, actually that indeed gives you the geometry, that's actually, again, this Hollywood-Iqbal-Wafa compactification of the resolved conifold. The reason I'm emphasizing this geometries appeared as S matrices for Chern-Simons theory, as well as of the refined Chern-Simons theory. So the question is, natural question is whether this kind of deformation, algebraic elliptic deformation, does it have anything to do with some further modification? We don't know yet, and maybe it's going to lead to something interesting. So thank you very much. Sure.
I missed some of your point, but what's the physical meaning of the P elliptic?
Oh, sorry. Okay, so the P is essentially, okay, so here, okay, let me just explain here. So if you have this is a Kähler class, let's say Q1, and when you compactify, as I said, there are two disks, and if you just put them together, you get another P1. So that's actually a torus made of two P1s attached on the poles. And that P becomes actually the whole Kähler class of the torus. So the elliptic parameter is literally the Kähler class of that elliptic vibration. Oh, sorry. Okay, also Sergey has a question. Yeah.
I wonder, so from 4D to 5D, you have this fiber-based changes.
Yeah.
Do you also experience another fiber-based changes when you go?
Actually, let me clarify on that. Okay, so fiber-based duality, or this exchange, is only in 5D. Actually, that actually makes age. Okay, I think that's the crucial thing. Why AGT is such. I mean, if in the 4D form, the original form, is very complicated, or to prove is very complicated. However, if you lift it to 5D, it just becomes relatively easy compared to what other people have done. And the reason is, if you are okay, so let me just go here. So if you are thinking in terms of this vibration, okay? If you want to go to 4D, you have to take a particular limit, what's called the field theory limit, where you actually treat the Kähler classes in the fiber and in the base differently. So one of them some of them are shrunk, and the other one are taken to infinite limit, volume limit. And that actually breaks the fiber-based duality. So that's why the instanton partition function of this, if you just do in 4D, look so much different from each other. However, if you go to the 5D, then these are just random, they are finite size P1s, and their role can be exchanged. And that exchange is the fiber-based duality. So actually, you lose that when you take the field theory limit and go to the 4D. And that's why it becomes so nice and so easy when you just lift it one dimension up. I think that's the cute thing, because the dual is not what AGT tells you. The dual is the fiber base, and you cannot see it in 4D.
I very much enjoyed your talk. I just had a light-hearted comment that I believe Japanese person you
Saito. Okay, sorry. So I apologize. Him, like, I'm very sorry. Like, yeah, I know the feeling. I also suffered a lot with my name, like Can and John and Khan. So I understand this sentiment. I apologize. Thank you. Thank you.
Didn't count as a question, but okay, then let's thank John again.
Thank you.